Welcome back, everyone. Ready to dive into something pretty fascinating. Today, we're going deep on unlabeled trees.
Oh, yeah, these are interesting.
Yeah, picture like networks, connections between points, but without needing to actually label any of the points.
Right, just the structure itself.
Yeah, exactly. Like mapping the bare structure of a complex molecule or, connections in a network. That's what we're talking about with unlabeled trees. And we're looking at sequence A00000055 from the OEIS.
The online encyclopedia of integer sequences.
Right, exactly. And this sequence tells us how many different unique unlabeled trees exist.
For any number of nodes you give it, yeah.
So like if we have, say, 5 points to connect, this sequence would tell us how many different ways we can link them up.
Without repeating the same structure, exactly.
Okay, so let's start with the basics, right? The first few terms of the sequence.
Okay, so if you just have one node, there's only one possible tree.
Right, just the node by itself.
Exactly, a lone point just hanging out there.
Okay, what about with 2 nodes?
With 2 nodes, well, you just connect them with a line.
Okay.
Still only one possible configuration there.
All right, and if we add a 3rd node?
You just extend that line, basically, again, only one unique tree.
So for 1, 2, or 3 nodes, it's pretty simple?
Yeah, very straightforward.
There's only one way to connect them without creating a cycle?
Exactly, you got it.
But then things get interesting when we get to 4 nodes, right?
Oh, yeah. That's where it starts to get fun. We have 2 distinct possibilities when you have 4 nodes.
2? How so?
Well, imagine a straight line of 4 nodes. That's one possibility, right? The other one is to have a central node with 3 branches coming off of it, like a star shape.
Ah, I see.
Those are 2 fundamentally different tree structures.
Okay, so with 4 nodes, we start to see those branching possibilities emerge.
Exactly.
And I'm guessing the number of possible trees just explodes as we add more nodes.
You are absolutely right. It grows incredibly fast with just 12 nodes. There are over 2 million unique unlabeled trees.
Oh, 2 million. That's hard to even fathom.
It is. It really shows the power of combinatorics, how even simple rules can generate this enormous number of possibilities.
That's incredible. It's like the number of potential network layouts
Yeah.
with just a dozen computers skyrockets.
Yeah, exactly.
So how do mathematicians even calculate these huge numbers?
Well, that's where these really cool mathematical tools come in, like generating functions.
Okay.
They're kind of like mathematical machines that have all the information about the entire sequence contained within them.
Okay.
The generating function for this sequence, A00000055, lets us calculate the number of trees for any number of nodes.
Wow. So we don't have to draw out millions of trees.
You don't have to, no.
That's pretty impressive.
Yeah.
Can you give us a simplified explanation of how a generating function works?
Sure. So think of it like it's kind of like a code that has all the information about the sequence stored within it. Each term in the sequence is represented by a specific part of the code.
Okay.
And by manipulating this code, we can extract information about any term, even for super large values.
So it's like a shortcut to get specific information about the sequence.
Exactly.
Without having to go through all the previous terms.
Exactly. It's a very elegant way to handle these things.
Okay. And is it just about calculating individual terms, or?
No, not at all. The generating function also lets us analyze the long-term behavior of the sequence
Interesting.
using what's called the asymptotic formula.
Okay, what does the asymptotic formula tell us about A000055 then?
So the asymptotic formula describes how the sequence grows as the number of nodes gets really, really large.
Okay.
It doesn't give you an exact value for every term,
Right.
but it shows you the overall trend.
Got it.
And for A000055, that trend is one of extremely rapid growth.
So even though we start with just one tree for 1, 2, or 3 nodes,
Right.
the formula is telling us that the number of unlabeled trees blows up way beyond what we can easily imagine.
Yeah, it gets big fast.
Okay. And so this sequence's behavior for larger values really highlights the inherent complexity in this seemingly simple idea.
Definitely. And what's even more interesting is that A000055 isn't isolated. It's actually interwoven with other sequences in the OEIS.
Right.
Each of them gives us insight into different aspects of unlabeled trees.
So like different perspectives on the same concept.
Yeah. And for example, the number of unlabeled trees can actually be expressed using a formula that involves the sequence for rooted trees.
Okay.
That's A000081, and another sequence called A217420.
So these seemingly separate sequences are all doing a mathematical dance together,
Yeah, they're all linked.
revealing these deeper connections in combinatorics.
Exactly. It's a beautiful illustration of how interconnected math really is.
Yeah, and how these seemingly separate concepts have these surprising relationships.
Absolutely. It's one of the things that makes math so fascinating.
Yeah, definitely. So we've got this one sequence connected to all these other mathematical ideas,
Oh, yeah, it's really quite amazing.
like discovering a hidden network beneath the surface of numbers.
I like that analogy.
And the connections don't stop at other sequences, right?
Not at all. The source material mentions these things called two-gonal two trees.
Okay.
And A000055 actually counts the number of those structures with n two-gons as well.
Two-gonal two trees. Sounds a little intimidating. What are those exactly?
Haha, yeah, it's a bit of a mouthful, but they're actually pretty simple to visualize.
Okay.
Imagine building with squares like you have tiles or building blocks.
Okay, like Legos.
Yeah, exactly like Legos. So you're connecting these squares edge to edge, and that's how you build a two-gonal two-tree.
Okay.
With each step, you add a new square, and you attach it to one of the existing squares along a single edge.
So you're building these chains of squares, but there's specific rules about how they connect.
Right. You can't have any overlaps.
Okay, so it's like a puzzle.
Yeah, that's a great way to think about it. And here's the really interesting part.
What's that?
The number of ways to build these two-gonal two trees with n squares is the same as the number of unlabeled trees with n nodes.
Whoa, that's an unexpected connection. It's like having two different sets of building blocks
Right.
that lead to the same number of possibilities.
Yeah, it really makes you think about what's going on underneath it all.
Yeah, the underlying math that connects these different structures.
Exactly. It's pretty mind-blowing, and there's even more.
Oh, there's more.
The source also talks about tree-perfect graphs.
Okay, another new term for us to unpack. What are tree-perfect graphs?
Right. So think of a tree-perfect graph as like a modified version of an unlabeled tree.
Okay.
You start with the basic unlabeled tree structure with the nodes connected by branches,
Right.
and then you add extra connection or shortcuts between any two nodes that share a common neighbor.
Oh, so you're making a denser network by adding these direct links.
Exactly. You're adding edges to create a more interconnected graph while still keeping that underlying tree-like structure.
Got it. And is there a connection to our sequence here, too?
Of course there is. The number of tree-perfect graphs with n nodes is also given by A00000055.
It's everywhere we look.
It is. It really is. It's quite remarkable.
So we've got unlabeled trees, two-gonal two trees, and tree-perfect graphs all linked together by this sequence.
Yeah, it's like they're all different sides of the same mathematical coin.
Yeah, different facets of the same idea,
Yeah.
and the connections don't stop there.
Nope, not even close. The OEIS entry even mentions a relationship with arrangements of non-intersecting circles on a sphere.
Circles on a sphere now? That sounds really abstract. How did that even relate to trees and graphs?
I know it sounds like a big jump, but it's actually pretty cool. So picture drawing circles on the surface of a sphere.
Like a balloon.
Yeah, exactly like a balloon, but none of the circles can overlap.
Okay, so you have these circles just scattered across the surface.
Right, and for n greater than 0, A000055 tells us the number of ways to arrange n-1 non-overlapping circles on a sphere.
So the number of ways to arrange those circles is directly related to the number of unlabeled trees.
It is. It's a deep connection between combinatorics, graph theory, and even geometry.
Wow, that's pretty amazing.
Yeah, these arrangements of circles, even though they look completely different from trees, share that fundamental structure captured by the sequence.
So 00000055 is like a hidden code,
I like that.
revealing these patterns across all these different mathematical landscapes.
It really is a remarkable sequence, and it makes you wonder what other secrets it holds. It's one of the things that makes exploring math so exciting. You know,
Definitely.
you never know what you're going to find, and it's a reminder that math is not just this collection of formulas.
Right.
It's a beautifully interconnected web of ideas.
Absolutely. It sounds like A00000055 could be a valuable tool for anyone working with networks, structures, or classifications.
Oh, absolutely. Anyone dealing with those kinds of things could benefit from understanding this sequence.
Speaking of classifications, the source also mentions a connection between A00000055 and classifications that require binary partitions.
Right. So this connection really highlights how unlabeled trees can represent these hierarchical classifications.
Okay, how does that work?
Well, a binary partition basically divides a set of items into two groups,
Okay.
and you repeat this process to create a tree-like structure
Got it.
where each node is like a subdivision.
So if you were classifying animals,
Mm-hmm.
you might start by dividing them into vertebrates and invertebrates.
Right, exactly. And then you further divide each group based on other characteristics.
Okay, so you're creating this branching structure
Yeah.
that reflects the relationships between the different categories.
Precisely. And guess what the number of possible classification schemes using n-1 binary partitions for n items is
our sequence.
our sequence A000055.
It's like a universal key,
It is.
unlocking patterns in all these areas of math.
It's amazing, isn't it? And it's a testament to how elegant math can be.
It is. It's really inspiring to see how these abstract ideas can have such far-reaching implications.
Yeah, it really shows you the power of theoretical exploration, you know?
Yeah.
It can lead to some pretty amazing advancements.
So we've been talking about this concept of an unlabeled tree, right? And it seems so simple, but it leads to this vast and intricate mathematical landscape. It's incredible.
It is. It's a great example of how something seemingly basic can have these far-reaching implications.
Exactly. And we've seen connections to graph theory, geometry, classification of information. It's all linked.
And the thing is, we've only just scratched the surface.
Oh, really?
Oh, yeah. The beauty of math is that every time you make a discovery, it seems to open up even more avenues to explore.
So where do we go from here then? What are some of the big unanswered questions or areas of active research?
Well, one area that researchers are really digging into is understanding the connections between unlabeled trees and other combinatorial structures even more deeply.
Okay.
You know, we've talked about those connections with two-gonal two trees and tree-perfect graphs and the circle arrangements, but there's still so much more to uncover.
So it's like mathematicians are trying to draw this map
Yeah.
of all the relationships between these different structures, and they're using A00000055 as their guide.
Exactly. It's like a giant puzzle where each piece is a different mathematical concept, and this sequence is giving us clues about how they all fit together.
That's a great analogy. Another area of research you mentioned is the computational side of things.
Right, because as you add more nodes, the number of possible trees just explodes.
It gets huge fast.
It does. It makes it really hard to even count them all, let alone analyze them.
Yeah, that makes sense. So mathematicians are coming up with algorithms and techniques to handle this massive amount of data.
Exactly. They're developing tools to help us explore the world of larger and larger unlabeled trees.
And are those tools helpful in other fields too?
Absolutely. They have applications in network analysis, optimization, data mining, pattern recognition, all sorts of areas.
It's amazing how something so theoretical can have such practical implications.
I know it's a great example of how abstract exploration can actually drive real-world progress.
Well, this deep dive has certainly been eye-opening for me.
It's been a fascinating journey.
It really has. We started with this simple idea of an unlabeled tree and ended up uncovering this incredible web of connections.
It's a reminder that math is all about those connections. It's a beautiful and elegant subject. And even though it can seem abstract at times, it can have a profound impact on our understanding of the world.
It definitely makes you appreciate the power of mathematical inquiry.
It does. And for anyone listening out there, keep exploring, keep asking questions, and keep marveling at the beauty of math. You never know what you might discover.
That's great advice. Thanks for joining me on this deep dive.
It was my pleasure.